Now, what we're going to look at is now, after having done reaction mechanisms, is that how do they tie into the idea of the rate of an equation? Now, the rate of an equation of an overall reaction is basically determined by what we call the rate determining step. And the rate determining step is basically the step in the multi-step process that you guys saw, 2 steps, 3 steps. So the rate determining step is one of those 3 or 2 steps, which is what we call the bottleneck, which slows everything else down. And therefore, then that determines the rate of reaction. And now we'll take a look at that in a little more detail in a bit. But first, I want to talk about a reaction we saw earlier, which was about X and Y. And I want to talk about rate orders, rate equations, and mechanisms first. And then go on to explain what I mean by rate determining step. Because honestly speaking, if you look at this example that I had shown earlier about 2x and 1y becoming z, we had come up with the fact that these must be the 2 steps. So these are 2 steps of the reaction where x2 is the intermediate. You'll notice, and they cancels out. And when you add their 2 steps, you get the overall equation. You do. The idea is that the reaction is determined by one of these 2 steps, the rate of the reaction. We call it the rate determining step. It's not that we add the rate of both the steps. It's that only one of these 2 steps will govern the overall rate of the reaction. But before we go to that and finding out how do we know that, what you need to realize that each step is individually a reaction itself. So each step should have its own rate equation too. So if I'm talking about step number 1, let's say I'm talking about step 1. Step 1 has its own rate equation. That is in line with what you can look from the equation, because step 1 really is X and X reacting. So if you remember in IGCSE and O levels, you've done that rate is proportional to concentration. What they were saying was rate is proportional to concentration in single step reactions, not overall reactions. This is the overall reaction for a multi-step reaction. Its rate equation cannot be judged by looking at the reaction. But for individual steps, when you only have 2 molecules involving, then the rate of individual steps can be determined by the individual steps, by just looking at the individual steps. So here, since step 1 involved X and X, the rate equation for step 1 would look like this. If you open this up, this will become rate equals to K into X square. That's step 1 for you. I need more space, so I'm going to do on the right also. What I mean to say is also, then step 2 can also have its rate equation. Because what is step 2? Step 2 is rate, which is proportional to the 2 reactants of step 2, x2 and y. So that's the rate equation for, or the rate relationship for step number 2, and this is the relationship for step number 1. So each equation has its own rate equation. Now, the only problem is that when you want to give rate equations for each step, you'd like to give the rate equations in terms of the original reactants. And x2 is an intermediate. So truly speaking, x2 should be given in terms of the original reactants. The funny thing is, x2 is made in the first step. So what molecules of the original reactants are responsible in making x2? Since the rate depends on the concentration of x2, whose concentration depends on what? The speed of the first reaction, doesn't it? So basically, really what you're saying is that the rate of the second step is really dependent on x, not x2, but the 2 x's that make x2 and y. So the rate equation for the second step is just simply x squared y, or rate equals to k into x squared and y. Obviously the 2 k's are different k's. The one on the left is k1 and this can be called k2. But again, we don't care about the actual value for k right now. We care about the relationship. So basically, each of these 2 equations steps has its own rate equation. And that's something to keep in mind. Each step can have its own rate equation. All right. Let me give you another example. Another two-step reaction mechanism whose rate equations will be a little different. So let's say if this reaction had a different mechanism, because it's still x2 y, and let's say that the first reaction, let's say the same reaction, 2x plus y, we found out that it's not two x's and one y first reacting to make z. Maybe we found out that step 1 was in fact x and y reacting to make z. And step 2 would be, sorry, not step 1 is not making z, x and y making xy. And in step 2, xy and more x makes z. You still get the same product, but now your xy is your intermediate. So the rate equation for step 1 would be what here? So rate equation for step 1 would be rate is equal to k into x into y. And the step 2's rate equation would be what? K into xy into x. But how did I make xy? From x and y in the first step, which will tell me that the rate equation for the second step is just simply x squared into y. So generally, if you notice, the rate equations for the earlier steps are smaller than rate equations for the latter steps. But each step can have its own rate equation. That's the first thing we'll notice. All right?
Quick pause. If you're finding value in this explanation, there's so much more to discover at Alt Academy, where we break down every A-level concept with the same clarity. Now back to the video lesson.
So now knowing that each step can have its own rate equation, the overall reaction's rate will be determined by one of these two steps. And the step that determines the rate for the overall reaction is called what? It's called the rate determining step. That's what we talked about earlier. So now the rate determining step is one of these two steps that in fact will have control the overall rate of reaction, because the overall rate of reaction isn't the individual steps. It'll have to be a different rate. It'll be one of the two individual steps. But let me explain what I'm saying. Let's go back to our first example. Now the first example we had x and x becoming x2 and x2 and y becoming z. And we had the two different rate equations for each of the steps. Like step 1's rate equation is x into x, x squared. Step 2's rate equation is x2 into y, which is x2 into y, but x2 came from two x's. So we already determined the two rate equations for the two steps. But if we find out that step 1 is slower than step 2, that makes step 1 the bottleneck. So what we find out is step 1 is slower than step 2. Therefore, according to our theory, that tells me that the step 1 is the rate determining step. Now, how do you understand why the slow step is the rate determining step? I'll explain that later. But if I have two steps, and we discover that one of those two steps is the slower step, that step becomes what we call the rate determining step. And the reason why it's called the rate determining step is because it will control the rate equation for the overall reaction. So what it means to be the rate determining step is that step is the rate equation for the overall reaction. So if step 1 is slow, then its rate equation is in fact the rate equation for the overall reaction. And that's why even though y is part of step 2, but step 2 isn't the rate determining step, step 1 is. So for the overall reaction, y isn't part of the rate equation. So y will have no effect on the overall rate. Y will have effect on the rate of step 2, but it will have no bearing on the overall rate of reaction, because the overall rate of reaction is determined by the rate determining step. I'll show you a couple of more examples. But in this particular case, if step 1 is the rate determining step, then this becomes a rate equation. Now on the other hand, what if I had said no. If I said okay, what we discovered is step 2 is slower. So if step 2 was slower, then the rate equation would have been this. Okay. So we have to uh, basically be told which is the slow step, because the slow step determines rate. So if step 1 is slow, the rate equation for that step is the overall rate equation. If step 2 is slow, the rate equation for that step is the overall rate of reaction. All right. So if I give you another example here, let us consider a reaction mechanism for A and 2B becoming C. So A and 2B becoming C could be that there are two B's reacting to make H, and then the H reacting with A to make C. H is the intermediate. So my reactants are A and 2B. Now if I'm told that step 2 is a slow step, so if I'm told that step 2 is a slow step, what I start doing is I will write the rate equation for step number 2. So what's the rate equation for step number 2? Well, its rate is proportional to H and A. But H is an intermediate whose concentration depends on the rate of the first step. And I want it in terms of my reactants. So which reactants are responsible for making H? And I look at H, I see two B's are responsible for making H. So that means B into B will make H. So my rate equation then becomes K into B square into A, or A into B square, however you like to write it. But this is if step 2 is slower. Yeah. So basically, in a multiple step process, each step has its own rate equation. But the overall rate equation, this is the overall rate. Overall is what you will find experimentally. The overall rate equation will be governed by the slowest step. And that step is known as the rate determining step. Okay. Now let's take a look at this reaction. This is between A, B, and C. Now we got three reactants, and now we got three steps, 1, 2, and 3. So only one of them determines rate. And so we got three different steps, A and B making E, which is an intermediate, gets used up, and E then makes G, which then reacts with another C to make the products. So now we are first to know the rate equation, the overall rate equation, we have to know what is my slowest step. So let's say I'm told that that's step number 2. So if step number 2 is my slowest step, that becomes my rate determining step, which means that the overall reactions rate is determined by the rate equation for step number 2. And step number 2 only has one reactant, E. So the rate is proportional to E. But I have to give my overall rate in terms of my reactants. And E is an intermediate. So what made E? So what made E was A and B. So my rate equation is K into A into B. And any reactant that comes after the slow step is never ever going to be part of the rate equation. That's why you've studied zero order reactions. If you notice here, C is a reactant, is not part of the rate equation, which means the order with respect to C is 0, or C is 0 order. And why? Because it is occurring after the slow step. So any reactant that occurs after the slow step is never going to be part of the rate equation. The reactants that come in or before the slow step either will be directly involved or will be responsible for making the intermediate. So they are a part of it, A and B. But C is after the slow step. It will never be therefore part of the rate equation. So the rate equation is simply the rate equation of the slowest step. All right. So one last example is this particular reaction between H2O2, H3O plus, and I minus. It takes place in 3 steps. These are actual molecules now, ions now. And the 3 steps add up to give you this full equation. And what we figured is the first step is the slowest of the 3 steps. It's slower than the other 2, which means that step 1 determines rate. So the rate equation for this would be what? Would simply be 1 H2O2 and 1 I minus, nothing else. That is it. And if you notice, H3O plus is a reactant, but is only coming in steps after the slow step. And another I minus, a second I minus, is also coming in after the slow step. So the only two particles that were involved in the slow step are going to determine the rate equation. So here, this is your rate equation for the overall reaction. And that's the one that you find experimentally. All right? So this is how mechanisms and rate determining step are basically connected to the overall rate equation, which you have been able to find experimentally. So the proof is through the reaction mechanisms. The slower step is what will give me the rate equation that we can discover experimentally. All right?
Hey there! If you found this A-level chemistry lesson helpful, why don't you head over to our website, altacademy.org, where you can sign up for the full A-level chemistry course. In addition to chemistry, you can sign up for physics, biology, math, or 4 other A-level subjects. Thousands of students have already taken the leap. What are you waiting for?